The Birth of a Black Hole. Introduction and the Mystery of Collapse, a journey into the unknown. Black holes remain some of the most enigmatic and fascinating objects in the known universe. Invisible to the naked eye, they are regions in spacetime where gravity becomes so intense that nothing, not even light, can escape their grasp. But how do black holes form? What happens at the end of a massive star's life that leads to the creation of one of nature as most extreme objects? And what can these cosmic phenomena teach us about the fundamental laws of physics? In this deep dive, we'll explore not only the astrophysical mechanisms behind black hole formation, but also the real-life experiments, mathematical models, and landmark scientific studies that have shaped our understanding of them. What is a black hole? Really, at its core, a black hole is a solution to Einstein's equations of general relativity, surrounded by an event horizon, the boundary beyond which no information can return. First predicted by Carl Schwarzschild in 1916, shortly after Einstein published his theory. A black hole is defined as a point in space where matter has collapsed into an infinitely dense singularity W. How the concept might sound abstract, black holes are now observed indirectly through several methods, including gravitational lensing, where light from distant stars bends around them, X-ray emissions from matter as it accelerates and heats up before falling in, gravitational wave detection, the ripples in spacetime caused by black hole collisions, first directly detected in 2015. That detection came from the LIGO scientific collaboration led by scientists like Kip Thorne, Rainer Weiss, and Barry Barish, who won the Nobel Prize in Physics in 2017 for confirming gravitational waves. Long predicted by Einstein, the death of massive stars, the beginning of a black hole, the most well-established formation mechanism for a black hole is the core collapse of a massive star. When a star roughly 20 to 25 times more massive than our Sun reaches the end of its nuclear fuel, it can no longer produce the outward radiation pressure necessary to counteract its own gravity. This internal tug-of-war is explained by the hydrostatic equilibrium principle, a balance between the inward force of gravity and the outward force from nuclear fusion. As long as the star is fueled, typically hydrogen and helium, it maintains stability. But once those fuel sources are exhausted and heavier elements like iron accumulate in the core, fusion ceases to be energy efficient. Iron, unlike lighter elements, does not release energy when fused. This is critical. In 1987, the supernova SN 1987A in the Large Magellanic Cloud gave astronomers the first real-time observation of a nearby massive star going supernova, the precursor stage to either a neutron star or a black hole. Although the exact remnant is still debated, the event provided unprecedented data confirming theoretical models of stellar death. Protons and electrons merge into neutrons in a process known as inverse beta decay, releasing a flood of neutrinos. The collapse mechanism: gravity wins once fusion stops. Gravity wins. The core begins to collapse under its own mass, compressing matter to extreme densities. This is where astrophysical modeling becomes essential. In a series of numerical simulations conducted by Hans Bethe and James Wilson in the late 1970s and 1980s at Los Alamos National Laboratory, they showed how the energy released in neutrinos during core collapse could trigger a rebound effect, creating a supernova explosion. If the remaining mass of the collapsed core exceeds the Tolman-Oppenheimer-Volkoff limit, around 2.2 to 2.5 solar masses, even the degeneracy pressure of neutrons is not enough to halt the collapse. At this point, the star no longer becomes a neutron star. It collapses into a black hole. This limit was developed from theoretical work by Richard Tolman, J. Robert Oppenheimer, and George Volkoff in the 1930s, combining Einstein's relativity with quantum mechanics of dense matter. Real-world black hole candidates. Observational evidence. While no one can see a black hole directly, we can observe their effects on nearby stars and gas clouds. One of the first serious candidates for a black hole was Cygnus X1, discovered in 1964. Astronomers like Tom Bolton and Louise Webster provided strong evidence in the 1970s that the object was too massive to be a neutron star, suggesting a black hole of around 15 solar masses. In more recent years, The Event Horizon Telescope (EHT) project captured the first image of a black hole, its shadow in 2019, the supermassive black hole at the center of the M87 galaxy. This image confirmed predictions made by general relativity and cemented the existence of black holes in the public imagination. Collapse physics. Black hole types and mass thresholds, the physics of stellar collapse. Step by step, let's take a closer look at what happens during a massive star's terminal collapse. After iron builds up in the stellar core, no further fusion reactions can release usable energy. The star's core is now supported only by electron degeneracy pressure, a quantum mechanical effect described by the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. But when the core exceeds the Chandrasekhar limit, approximately 1 point for solar masses, electron degeneracy pressure fails to support the star against gravity. This limit, formulated by Indian astrophysicist Subrahmanyan Chandrasekhar in 1931, marks the boundary between white dwarf formation and catastrophic collapse. Once this threshold is passed, the core contracts rapidly, and photodisintegration occurs. Gamma rays break iron nuclei into lighter particles, consuming energy instead of releasing it. Electron capture. Protons combine with electrons to form neutrons and neutrinos. These processes reduce pressure and accelerate collapse. If the resulting core is between approximately 1.4 and approximately 2.2 solar masses, a neutron star may form. But if it exceeds the Tolman-Oppenheimer-Volkoff limit, TOV limit, collapse becomes unstoppable, forming a black hole. Neutron stars versus black holes. What's the deciding factor? The decisive factor is mass. White dwarf. Final product: if the core mass is less than 1 point for solar masses, neutron star forms between approximately 1.4 and approximately 2.2 solar masses. Black hole results when the core exceeds approximately 2.2 solar masses. In 2020, a landmark gravitational wave event GW190814, observed by LIGO, Virgo, revealed a merger between a black hole, approximately 23 solar masses, and an object around 2.6 solar masses. This challenged previous mass boundary assumptions and sparked debates over the precise limits of neutron star formation. Was the smaller object a heavy neutron star or a light black hole? The answer remains unresolved, but the event helped refine mass thresholds and pushed models of stellar evolution further. Types of black holes. More than one path to darkness. Black holes come in several classes, depending on their mass and origin. 1. Stellar mass black holes, formed through the core collapse process we discussed. Typical mass range, 5 to 30 solar masses. Confirmed via X-ray binaries, e.g., Cygnus X1. V4O for Cygni. 2. Intermediate mass black holes, IMBs. Mass range, 100 to 100,000 solar masses. These are theorized to form through successive stellar collisions or runaway mergers in star clusters. Evidence remains sparse, but in 2020, LIGO, Virgo reported GW1905-1, a merger event creating approximately 142 solar mass black hole, the first strong candidate for an IMB-H3. Supermassive black holes, SMBs. Mass range, millions to billions of solar masses, found at the centers of most galaxies, including the Milky Way's Sagittarius asterisk to 4 million solar masses. Their origin is still unclear. Hypotheses include early formation from direct collapse of massive gas clouds, growth through accretion, and galactic mergers seeded by early population. 3 stars. The James Webb Space Telescope JWST is expected to shed more light on this mystery by peering into the early universe and tracking SMBH growth, accretion, and spin. The engines of activity. Once formed, black holes don't just sit quietly, confirming that much of the matter falls in at low rates and is ejected or heated before crossing the event horizon. Supporting models like advection-dominated accretion flows, ADAFs, they often feed on surrounding gas and stars through an accretion disk, a spinning, superheated swirl of matter emitting intense X-rays. Spin affects the shape of the event horizon and the efficiency of energy extraction via mechanisms like the Penrose process or Blandford's Nyack effect. both central to high-energy astrophysics. This process powers active galactic nuclei, agings, and quasars, the brightest objects in the universe. In 2000, NASA's Chandra X-ray Observatory studied the accretion flow around Sagittarius asterisk. Also, black holes can spin, a property quantified by the Kerr metric, a solution to Einstein's equations discovered by Roy Kerr in 1963. Simulating collapse, from theory to supercomputers. Understanding black hole formation today relies heavily on numerical simulations. Projects like FLASH, developed at the University of Chicago, and the Einstein Toolkit simulate core collapse supernovae using relativistic hydrodynamics, neutrino transport, and nuclear reaction networks. These models predict whether collapse leads to a neutron star or black hole. Simulate gravitational wave signatures for LIGO. Test the impact of rotation, magnetic fields, and metallicity on the collapse outcome. In a 2016 paper, Ott et al. Used simulations to show that rapidly rotating stars produce stronger gravitational waves, helping refine detection strategies. Event horizons, singularities, and cosmic consequences. The event horizon, the no-return point. One of the most iconic features of a black hole is its event horizon, the boundary at which escape becomes impossible. Once any object crosses this threshold, not even light can return. The term was first used in this context by physicist Wolfgang Rindler. In the 1950s, the radius of the event horizon is known as the Schwarzschild radius, named after Karl Schwarzschild, who in 1916 solved Einstein's field equations for a non-rotating, uncharged mass. This radius is given by the equation, or is equals to g(m)c, to where g is the gravitational constant, m is the mass of the object, c is the speed of light for Sagittarius A asterisk. The radius is about 12 million kilometers. For a black hole with the mass of our Sun, this radius is about 3 kilometers. What happens inside the event horizon? According to classical general relativity, everything collapses toward a point of infinite density and zero volume, the singularity. Singularities. Physics at the edge of understanding the singularity is where our known laws of physics break down, where it represents a region where gravity becomes infinite and space-time curvature becomes undefined. In 1965, Roger Penrose proved mathematically, using topological techniques, that singularities are a natural outcome of gravitational collapse under very general conditions. This result was so groundbreaking that Penrose received the 2020 Nobel Prize in Physics. Penrose's singularity theorem, developed with Stephen Hawking, implied that the formation of singularities wasn't just a theoretical oddity. It was inevitable if general relativity held true and matter collapsed beyond a critical density. However, most physicists now believe that a full understanding of singularities will require a quantum theory of gravity, possibly from string theory or loop quantum gravity, neither of which has been experimentally confirmed. Black holes and time. A one-way journey. Black holes dramatically affect not only space, but time. This bizarre property has been explored both in theoretical physics and in popular media, such as Christopher Nolan's Interstellar, which consulted physicist Kip Thorne to model time dilation accurately near a rotating black hole. Near a black hole, gravitational time dilation occurs, a prediction of general relativity confirmed by numerous satellite experiments, including those by the Gravity Probe mission in 1976. The closer you get to the event horizon, the slower time flows relative to an outside observer. At the horizon itself, time appears to stop from the viewpoint of someone far away. Supermassive black holes and galactic evolution. This suggests they formed very early in cosmic history, while stellar black holes result from dying stars. Supermassive black holes SMBs lie at the hearts of most galaxies. Their mass can reach billions of solar masses, and their formation is still a subject of intense research. Recent breakthroughs using the James Webb Space Telescope JWST and ALMA Observatory have found quasars, active SMBs, less than 700 million years after the Big Bang. So how did they get so big so fast? Use simulations to suggest that direct collapse black holes could reach SMBH status in less than a billion years if conditions in the early universe were right. Proposed theories. Direct collapse. Massive gas clouds collapsing directly without forming stars. Rapid accretion, feeding on enormous amounts of gas and matter. Black hole mergers. Smaller black holes combining over time. Proposed that feedback from SMBs could solve the cooling flow problem in galaxy formation models, preventing galaxies from growing too large too fast. A 2021 study published in Nature Astronomy led by Fabio Pacucci and Avi Loeb of Harvard. Black holes shape galaxies and are thought to be powered by spinning black holes, interacting with magnetic fields, described by the Blandford-Nyack mechanism. Beyond being gravitational monsters, black holes have a cosmic impact. Through feedback mechanisms, such as radiation pressure and relativistic jets, SMBs can regulate star formation in galaxies. These jets, observed in systems like Messier 87, can extend hundreds of thousands of light-years in a 2006 paper published in Monthly Notices of the Royal Astronomical Society, Croton et al. Thus, black holes are not merely cosmic endpoints. They are central actors in the story of galaxy evolution. Quantum black holes. Hawking radiation and the information paradox where gravity meets quantum mechanics. While general relativity explains black holes remarkably well on large scales, it breaks down near the singularity, where densities and curvatures become infinite. To fully understand black holes, we must reconcile gravity with quantum mechanics, the theory governing the subatomic world. This frontier has given birth to quantum black hole physics, a field where some of the most profound paradoxes in theoretical physics have emerged. Hawking radiation. Black holes aren't forever. In 1974, Stephen Hawking combined quantum field theory with curved spacetime and made a stunning prediction. Black holes can emit radiation. Using principles from quantum mechanics and the Heisenberg uncertainty principle, Hawking showed that particle-antiparticle pairs constantly pop in and out of existence near the event horizon. Occasionally, one particle falls in while the other escapes. From an outside perspective, this appears as radiation leaking from the black hole. This phenomenon, now known as Hawking radiation, means that black holes lose mass over time, eventually evaporating completely, where T equals dCe8 gmkBT is the black hole's temperature, m is its mass. As the reduced Planck constant stellar mass and supermassive black holes radiate extremely slowly. But primordial black holes, tiny ones potentially formed just after the Big Bang, could evaporate within the lifetime of the universe, and their final burst of energy might be detectable as gamma-ray flashes. Kb is Boltzmann's constant. The smaller the black hole, the hotter and faster it evaporates. NASA's Fermi Gamma-Ray Space Telescope has searched for these signatures, though no conclusive evidence has yet been found. The black hole information paradox and Hawking radiation appears purely thermal, containing no record of what fell in. Hawking radiation leads to one of the most significant unsolved puzzles in theoretical physics. If a black hole evaporates completely, what happens to the information about the matter that fell into it? According to quantum mechanics, information cannot be destroyed. But general relativity implies that once matter crosses the event horizon, its information is lost to the singularity. This challenges the no-drama principle of general relativity. This creates the black hole information paradox, a clash between the two most successful theories. In physics, over the past decades, many proposed solutions have emerged. Holographic principle, proposed by Gerard T. Hooft and Leonard Susskind. This idea suggests that all information falling into a black hole is encoded on its 2D event horizon, much like a hologram stores a 3D image on a 2D surface. Firewall hypothesis, proposed by Almheri, Merolf, Polchinski, and Sully Amps in 2012. It suggests a violent firewall at the event horizon that burns up information. Soft hair and quantum hair. In 2016, Stephen Hawking, Malcolm Perry, and Andrew Strominger proposed that black holes have soft hair. Quantum information stored in low-energy quantum excitations. On the horizon, it will detect low-frequency gravitational waves from supermassive black hole, EMI or GERs, ideal for probing strong gravity regimes. While none of these theories has been experimentally confirmed, They mark real progress toward a quantum theory of gravity. Future observations, gravitational waves, and quantum tests. In 2015, the LIGO Observatory made history by detecting gravitational waves from a black hole merger. Since then, dozens of such events have been observed, opening a new era of black hole astronomy. Upcoming missions and observatories will help test quantum effects. LISA, Laser Interferometer Space Antenna, ESA. NASA missions set to launch in the 2030s. James Webb Space Telescope JWST, already observing distant quasars and SMBs in the early universe, providing clues to their formation and evolution. Einstein Telescope and Cosmic Explorer, next-generation ground-based detectors, expected to increase sensitivity to black hole ring downs, potentially testing the Noether theorem. The idea that black holes can be described only by mass, charge, and spin, simulating the quantum realm, the role of supercomputers. To bridge general relativity and quantum mechanics, physicists use quantum gravity simulations. Projects like Loop Quantum Gravity, NADS, CFT duality, anti-de Sitter space, conformal field theory, rooted in string theory, are being tested via numerical models. In 2023, researchers from MIT and Caltech use quantum circuits to simulate black hole evaporation, providing evidence that information might leak out slowly in subtle correlations, not as pure thermal radiation. While these studies are in early stages, they show promise in resolving the paradox. What black holes reveal about the universe? Black holes as cosmic laboratories. Black holes are more than just astrophysical oddities. They serve as natural laboratories for the most extreme conditions in the universe. They test the boundaries of our understanding of gravitational physics via general relativity, thermodynamics, via entropy and temperature relationships, quantum mechanics via information paradoxes, and Hawking radiation. In fact, black holes are the only objects known to combine all four fundamental forces of nature: gravity, dominant at the macroscopic scale, electromagnetism, and charged black hole, strong nuclear force during stellar core collapse, weak nuclear force during neutrino production in supernovae. This makes them unique tools for pushing the frontier toward a theory of everything, a unified framework for all physical laws. The laws of black hole thermodynamics. The analogy between black holes and thermodynamics isn't just poetic, it's mathematically real. In the 1970s, Jacob Bekenstein proposed that black holes must have entropy proportional to the area of their event horizon, not volume. Hawking later confirmed this when he discovered that black holes radiate. This led to the formulation of the four laws of black hole thermodynamics, which parallel classical thermodynamic laws. Thermodynamic law, black hole analog, Zeroth law. Thermal equilibrium, surface gravity is constant on the horizon. First law, energy conservation equals plus, dm equals TdS plus, mass relates to entropy. Second law, entropy increases horizon area never decreases. Third law, absolute zero unreachable. No process can reduce surface gravity to zero. This insight hinted at a deep connection between gravity and entropy, still one of the greatest unsolved mysteries in theoretical physics. Philosophical implications. What is reality? Black holes challenge our intuition not just scientifically, but philosophically. If information truly disappears in a black hole, does it violate the conservation of information, a bedrock of quantum theory? What happens to causality inside the event horizon? Could black holes be gateways to other universes or wormholes, as suggested by the Einstein-Rosen bridge model? These questions push us beyond science and into the realm of metaphysics, asking what it means to observe, measure, and know in a universe governed by probabilistic quantum events and curved space-time. Where we go from here, the future of black hole research. We are entering a golden age of black hole discovery. James Webb Space Telescope JWST is unveiling early supermassive black holes, formed less than 1 billion years after the Big Bang. LIGO, Virgo, and soon LISA are detecting gravitational waves, literal ripples in spacetime, from black hole collisions. Event Horizon Telescope continues refining its imaging of black hole shadows, with future targets including Sagittarius A** and M87's jet dynamics. Simulations from exascale supercomputers are providing new models of accretion disks, magnetic fields, and quantum-scale behavior near singularities. Meanwhile, theoretical physicists are building bridges between string theory, holography, and quantum information theory, revealing new ways to think about spacetime itself. As Nobel laureate Subrahmanyan Chandrasekhar once said, "The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time." Final thoughts. Why black holes matter but to scientists? They are keys to understanding everything. To the casual observer, black holes may seem like distant curiosities. How stars live and die, how galaxies form and evolve, how gravity shapes the fabric of the cosmos, and maybe, just maybe, how to unify the laws of physics, their formation, from the collapse of massive stars, marks both an end and a beginning. And among them may lie a black hole, silent and visible, but telling a story that may one day reveal the ultimate truths of reality. In many ways, understanding how black holes are born helps us better understand how our own universe was born. From singularity to spacetime, from the void to the structure we now see. So, the next time you look up at the night sky, remember, out there, hidden in the vastness of space, are the quiet remnants of stars that once shone bright. If you enjoyed this deep dive into the birth of black holes, be sure to like, subscribe, and hit the bell icon. We have new space science videos every week that bring the cosmos closer to home. Thanks for watching, and keep reaching for the stars.